Welcome to the final problem solving session of General Physics 2. This one involved looking at problems dealing with lenses, and the two equations that we basically use to solve all of these problems are the thin lens equation, which is identical to the mirror equation, and the magnification equation as well. So problem 1 reads a converging lens with a focal length of 90 centimeters forms an image of a 3.2 centimeter tall real object that is to the left of the lens. The image is 4.5 centimeters tall and inverted. So we want to know where the image is located in relation to the lens. Is the image real or virtual? And how far apart are the object and the image? Well, we can approach this entirely algebraically if we wish to do so, but we can also think about what's happening here with what we've done from ray tracing exercises before, and I prefer the latter, to think about this rather than just plugging in and getting some numbers. So if I have a converging lens and I have an object that is closer to the lens than the focal length, we've done ray tracing exercises to show that I get a virtual image that is upright and larger than the original object and on the same side of the lens as the object is. Whereas if I have a converging lens and my focal point's there and my object is outside of the focal length of that lens, in this situation we get an image formed over on the other side that's a real image that is inverted and maybe larger or smaller than the original object depending on how close things are to the various focal points. So when I read this and I read that I have an image that's 4.5 centimeters tall and inverted, right away it cues me in that I have this situation and that I have a real image, but we can back that up with the math here as well. So where is the image located in relation to the lens? Well, I have my thin lens equation, which says that 1 over the focal length equals 1 over the object distance plus 1 over the image distance. But it seems like I have two unknowns in this situation because I don't know the object distance and I don't know the image distance. However, the fact that I know the two heights is going to help me here because the magnification relates the image height to the object height, but it also relates the ratio of the image distance to the object distance with a negative sign in there. And that means if I'm looking for the image distance in here, I'm going to solve this part of the magnification equation for the object distance. So the object distance is going to equal the negative of the ratio of image height to object height times the image distance. And that piece can be plugged in over here for my object distance. If I do so, then I get an expression that says 1 over the focal length equals 1 over the negative of the image height to the object height times the image distance plus 1 over the image distance. And looks a little bit messy, but now I have just one unknown in this expression. So we can rewrite this a little bit. If we pull 1 over the image distance out of both of those terms and flip this, I'll have minus the object height over the image height plus 1. And that means the image distance is equal to the focal length times that expression in the brackets there. So we can go ahead and plug in numbers. We're told that the focal length is 90 centimeters. The object height is 3.2 centimeters. The image height is 4.5 centimeters plus 1. And if I punch that all into my calculator, I get that the image distance is 217 centimeters. Question B, is the image real or virtual? Well, a couple of things. I've already reasoned about it before and argued that it's probably a real image. But also the fact that I solve for the image distance and I get a positive quantity right here tells me as well that this is a real image. If I got a negative value for the image distance, that would be a key that it is a virtual image. Question C says, how far apart are the object and the image? So we know that this distance right here is 217 centimeters. We need to know this distance, which is the object distance, in order to get this full distance between the object and its image. And if I could go back to my thin lens equation and solve for it, I think it's a little bit easier to just go to this expression that we got from the magnification equation. The object distance is the negative of the image height over the object height times the image distance, and if we plug in there, the image is 4.5 centimeters tall, but it's inverted, so that's a negative image height. The object is 3.2 centimeters tall, and then I multiply that by the 217 centimeters. I get 154 centimeters. And that 154 centimeters here, plus the 217 centimeters, gives me a total distance between the two of 371 centimeters. Second problem, an object is 16 centimeters to the left of a lens. The lens forms an image that is 36 centimeters to the right of the lens. What is the focal length of the lens? Well, we can solve that directly with the thin lens equation. 1 over the focal length is 1 over the object distance plus 1 over the image distance. So that means the focal length is that sum inverted. If we go ahead and plug in numbers there, 1 over the object distance of 16 centimeters plus 1 over the image distance of 36 centimeters, all inverted, gives us just over 11 centimeters for the focal length. Is the lens converging or diverging? Well, the answer that we just got for A tells us that it's converging. Converging lenses have positive focal lengths and diverging lenses have negative focal lengths. But the other reason I know it is the object's to the left of the lens and the image is to the right of the lens, and only converging lenses can make that happen. Diverging lenses always produce virtual images, and those virtual images are always on the same side of the lens as the object is located, just in a different location on that lens. So this is a converging lens. If the object is 8 millimeters tall, how tall is the image? Again, from our magnification equation, we know that the ratio of the image height to the object height is the negative ratio of the image distance to the object distance. And that means the image is that negative ratio times the object height. So that's negative 36 centimeters for the image, 16 centimeters for the object, and 8 millimeters. I don't need all my units to match here because centimeters is going to cancel out with centimeters, and I'm going to find a final image location that is in units of millimeters. And if I plug that in, I get negative 18 millimeters. That tells me that the image is 18 millimeters tall, but the fact that it's negative tells me that this image is inverted relative to the regular object. So I have a situation where I have a lens, somewhere over here is the object, and then somewhere over here further away from the lens is the inverted image of that object produced by that lens. The third problem uses the same type of analysis, but this is illustrating what we can do when we have two lenses in a system. So it reads, when two lenses are used in combination, the first one forms an image that then serves as the object for the second lens. The magnification of the combination is the ratio of the height of the final image to the height of the object. A 2 centimeter tall object is 57 centimeters to the left of a converging lens that has a focal length of 40 centimeters. A second converging lens, this one having a focal length of 60 centimeters, is located 300 centimeters to the right of the first lens along the same optic axis. Again, you don't have to draw a picture, but there's a heck of a lot of information to be keeping track of in this situation. So I'm going to go ahead and sketch this. So I got one lens here. I got another lens over here. And these are 300 centimeters apart. And the focal length of lens number 1 is 40 centimeters. Focal length of lens number 2 is 60 centimeters. And the 2 centimeter tall object is 57 centimeters to the left here. So this is not going to be to scale horizontally and vertically, but this is 2 centimeters tall, and this distance right here is 57 centimeters. So like we do so often in physics, we're going to solve this with superposition kind of thinking. In other words, find the effect of one lens, ignoring the second lens, and then find the effect of that through the second lens, and then put both of those two results together to get my final answer. So I'm just going to ignore this lens on the right for the time being and find the location and the height of the image formed by the first lens, as part A asks me to do. So again, if you rearrange that thin lens equation, you're going to get that the image distance is 1 over the focal length minus 1 over the object distance, all inverted. And if we go ahead and plug in the numbers there, we've got 1 over 40 centimeters minus 1 over 57 centimeters. Invert all of that, and if you calculate that, it's about 134 centimeters. The image height is going to be the negative of the ratio of the image distance to the object distance times the object height. So that's negative 134 centimeters over 57 centimeters times that 2 centimeter height. Punching that out gives me a minus 4.7 centimeter image height. So I know the image is formed 134 centimeters away from lens number 1, so somewhere in this neighborhood. It's taller than the original object, and the negative is telling me that it's upside down. So somewhere in this vicinity is where I get my image from lens number 1. And this distance right here is 134 centimeters. So now to do part 2, where I want to know the image formed by lens number 2, I'm essentially ignoring lens number 1, and I'm treating this image from lens number 1 as the object for lens number 2. Since this is 134 centimeters and the lens to lens distance is 300 centimeters, this means this is 166 centimeters from lens number 2. And I use that to do my new image calculation. So the new focal length for lens number 2 is 60 centimeters. My new object distance is that 166 centimeters. Got to take the inverse of all of that to figure out the new image distance, and that works out to be 94 centimeters. It's a positive value, so I know that it is over here to the right of this lens. And the image height here is the negative of the image distance. 94 centimeters is my new image distance. Over the distance to the object, that's my 166 centimeters. And this object, the intermediate image here, was 4.7 centimeters tall. But if I put the negative in there, I'm going to end up getting a positive value for this final image height. And that tells me that the final image here is on the same side of the optical axis that my original object was. So this is probably not super to scale, but my final image is over here to the right of both lenses, 94 centimeters from lens number 2, and 2.66 centimeters tall. So you can use this for any number of lenses. You just find the result through one lens, then find the result through the next lens, and find the result through the next lens, and it will ultimately predict the location of the final image in that system. The final two questions we looked at involved vision correction, and if you're anything like me, this is a topic of interest because your vision may be being corrected as we speak. I'm personally nearsighted, and so I have to use corrective lenses to solve that. Others are farsighted. When you're nearsighted, that means you can see things fairly close to your unaided eye clearly, but things that are far away are difficult to see, and that's often called myopia. That's the more technical term. Farsightedness means I can see things further away clearly, but not close to me, and that is hyperopia. So in this particular question, it reads, ordinary glasses are worn in front of the eye and usually 2 centimeters in front of the eyeball. A certain person can see distant objects well, but his near point is 50 centimeters from his eyes instead of the usual 25 centimeters. So distance objects well, that's my cue that this person is farsighted or hyperopic. And to correct hyperopia, you need to use a diverging lens. Suppose his near point is 50 centimeters from the eye instead of the usual 25 centimeters. So let's draw a little sketch. So here is a eyeball of this person looking. They are going to use a diverging lens to help correct the vision problems. And what you want to do then is you want to take something that is actually 25 centimeters away. So if you have a piece of paper that you're trying to read here, and it is 25 centimeters away from the eye, you want to use the lens to produce an image back here at the near point, the actual near point of 50 centimeters, because your eye can see things at 50 centimeters clearly. So if the eye to the image distance is 50 centimeters, and the eye to the object you're actually looking at distance is 25 centimeters, that means that the distance from the object to the lens that we're using to correct here is 23 centimeters, and the distance from the lens to the image we're producing is 48 centimeters. So I know both the object distance and the image distance. I can use that to calculate the focal length using the thin lens equation. So the focal length is 1 over, let's see, my object distance is 23 centimeters, and my image distance is 48 centimeters, but it's negative because I want to use this lens. Well, diverging lenses only form virtual images, but both corrective lenses are used to form virtual images to make the object appear to be in a different location to your eye than it actually is. And the inverse of that will give me the focal length. So if I plug in those numbers, I find the focal length is 44.2 centimeters. What is their power in diopters? Well, if you've been to the eye doctor, if you have any sort of vision problems, they're not going to say, oh, your eyes are this bad and you need a lens with this focal length. Instead, they prescribe it in a power, and the power is 1 over a focal length if that focal length is measured in meters. So our focal length here is 44.2 centimeters. That's 0.442 meters, and 1 over 0.442 is 2.26. It is a positive value corresponding to the diverging lens. And so if you are farsighted, the power that the optometrist is going to prescribe for you, again, is that inverse of that focal length, and it'll be a positive number. I do not think any eye doctors go to the hundredths place. Usually the powers jump by a quarter, and so it's like 2 or 2.25 or 2.5, etc. Number 5 was kind of a similar problem, but now it's contact lenses, and they're right on the eyeball. So the distance from the eye to an object or image is the same as the distance from the lens to that object or image, and a certain person can see near objects well, but her far point is 85 centimeters. Near objects well is code for this person is nearsighted. Nearsighted is also known as myopia, and so this is a myopic person. And in order to correct myopia, myopia is a condition where the lens on your eye is bending light too much. And so in order to correct that, we need to use a diverging lens, which makes me realize that I did the previous problem wrong. Everything's right in here except for the kind of lens. I need to use a converging lens. And I should have cued into that to the fact that the focal length is a positive value in that previous situation. All right, back to the contact lens. If I have a nearsightedness, I correct that with a diverging lens. And so we're going to wear contact lenses. So here's our eyeball on this person. And we're going to put a diverging lens on there. You don't see it, like the diverging lenses we use in lab, but to make the diverging lens, you just need the bottom and the top of that lens to be thicker than the middle, and you'll get that diverging effect there. We have a far point of 85 centimeters, but we can see near objects well. That means we want this person to be able to take something that is very far away, like this incredibly drawn pine tree, and make it appear as if it is 85 centimeters away as a virtual image. So the actual distance, very far, we want to bring that in and make it appear like it's 85 centimeters away. What focal length of the lenses is going to be needed here? Well, we're going to use our same approach. 1 over the focal length is 1 over the object distance plus 1 over the image distance. And in reality, the answer is going to change a little bit depending on what you plug in for that object distance. But I read very far as Q4. Let's use infinity here. And we want to make this a virtual image that is 85 centimeters away. So I'm going to put in my image distance of 85 centimeters, but because it's a virtual image, that's negative. 1 over infinity is 0, so that means the focal length needs to be negative 85 centimeters for this particular individual. The negative is telling me the diverging lens. What power does this represent? Well, power again is 1 over the focal length measured in meters. So if we do 1 over negative 0.85 meters, we find that the corrective power is negative 1.17. This is, I think, often given the unit diopters, but it's inverse meters. And again, your optometrist is not going to have this exact prescription. This person would probably get a minus 1.25 prescription, which is not super nearsighted. I personally am in minus 5.25 range, so I'm significantly more nearsighted than this nameless individual. All right, those are the problems that we looked at in terms of problem solving dealing with lenses. This is sort of the more algebraic approach, and the workbook works on the geometric approach for solving similar problems. As always, if you have questions after this, or if noticed an error that I didn't correct, like the one I did correct on problem 4 a little late in the game, I'd appreciate hearing about it. Thanks a lot.